Welcome back everyone. In the last lecture, we had seen how to characterize controllable subspaces of a system. We saw that the image of the controllability Gramian gives you the controllable space of a system. We also saw how to find out control inputs that you take you from an initial state to a final state within a fixed time. Today, we would be diving into controller design related to such systems. We will try to see how can we design what is known as state feedback controller for a system. Remember, in the classical control case, we had designed PID controllers where the output of the system was fed back into the open loop system so that we could compute the error between the reference and the output, and using that error signal as input to the PID controller, we used to control the output of the plant. In this case, we would not be doing something like that. Here, we would feed back the states of the system and try to get to a trajectory that we desire. Recall this example in which we had found out the step response of the system and the state response came out to be of this form. Now, I can ask the question, is it possible for me to make the state response depend on an exponential term of the form e to the power of minus t or maybe of the form e to the power of minus 100 t. Notice that the state response solution here depends, the rest of the terms are all constants, but one of the term here is e to the power of minus 2 t, okay? And this is the term that actually governs how it will behave as t increases, right. So, if I want to change this term, I will have to go ahead and change this matrix itself somehow. And one more important thing to note here is that you will see the power of the exponential term here is nothing but the eigenvalues of this state matrix. So, if I change the eigenvalues of the state matrix, then I would be able to influence the state trajectories as we want. In other words, I want the state trajectories to have terms like e to the power of minus t, which means that I would want that my state matrix here must be somehow changed to have an eigenvalue of minus 1. Now, how can we achieve that? So, the question is, suppose I want that the trajectory should decay slower or faster maybe, then I will have to change the eigenvalues of the matrix A. This can be done using a technique called the state feedback control. So, we will come up with a controller that will help me to change the state trajectories response. So, if I consider a controller of the form u equal to minus k1 k2 x, suppose I use this expression and I plug it into this system. Okay. So, what will happen? Let us look at that. So, if I plug this into the system, then u gets replaced by this expression, and then you can multiply, this is a 2 cross 1 matrix, this is a 1 cross 2 matrix, I can multiply this part out, this will become a 2 cross 2 matrix. So, we will have something of this form. Now, notice k1 and k2 can be changed arbitrarily, we can change it, it is in our hands, right. So, I can go ahead and change the value of k1 and k2. If I change the value of k1 and k2, the eigenvalues of this matrix will change, right, and that is what we wanted to do. So, basically the idea is that if we change the value of k1 and k2 in such a way that, suppose let me call this a hat, suppose the determinant of Si minus a hat is exactly S plus 1 and say S plus 100, then I know that the eigenvalues of this matrix will be minus 1 and minus 100, and in that case when I solve this differential equation x dot equal to this matrix x plus r, if I solve this differential equation, then I will get, in that case I will get solutions which will have the terms e to the power of minus t and e to the power of minus 100 t. Now, this was an easy problem in the sense that this matrix here, the matrix given here is a 2 cross 2 matrix, and for a 2 cross 2 matrix it is very easy to find out determinant of Si minus A hat. However, think about the case when suppose you have a system which has more than 2 states, suppose it has 100 states. In that case the A matrix will become a 100 cross 100 matrix. And think about the situation where you have to find out determinant of Si minus A hat, where A hat is a matrix of this form where A hat will also be 100 cross 100 then. So, the determinant of Si minus A hat will be a polynomial which will have degree 100. Finding that out and then again finding the roots of that will become a tedious job, right. So, there has to be some way by which I can simplify this problem and solve this easily, and that is the idea that we are going to discuss next. So, the question that we are asking is, how can we place eigenvalues for controllable seesaw systems? In this entire discussion that I will do today, I will consider that the system is completely controllable, and of course, we are dealing with seesaw systems here. Now, the question I am asking is, how is it possible to find out this u or the control law by which the eigenvalues of the actual state matrix or the state matrix of the plant can be changed. So, we will use again this idea of transformations. Remember, we have been using this quite a lot. So, we used it to find out Jordan and diagonal forms, right. We had used this idea to find out the Jordan and diagonal forms, so that we can get to the state response of the system. In that case, the T matrix was either coming from eigenvectors or was coming from generalized eigenvectors. Now, we would get to another canonical form, okay, not the diagonal or Jordan canonical form, but another canonical form that will make this problem of placing eigenvalues or changing eigenvalues of the matrix A easy for us. Let us see how are we going to change the eigenvalues for the system. Okay. Let us see that. So, we will have to choose a transformation matrix T here, which will take the matrix A hat, which is A hat is here, to a nice form. So, this is the recipe to do that. Let us say that the characteristic polynomial of the matrix is this, okay, of this A matrix is this. Again, let me recall that the characteristic polynomial of A and the characteristic polynomial of A hat are the same, because determinant of Si minus A can be written as determinant of T inverse T minus T inverse A hat T, and then I can write it down as determinant of T inverse determinant of Si minus A hat determinant of T, and these two will cancel out. So, I will be left with determinant of Si minus A hat. So, the eigenvalues of the matrix A and the eigenvalues of the matrix A hat are the same. In other words, the characteristic polynomial of A and the characteristic polynomial of A hat are the same. So, let us say that the characteristic polynomial of A is this. Okay. Now, we will form a transformation of the form P, which will be equal to T inverse. See, we wanted to find out a T, so we are defining T inverse instead of T. Okay. How are we defining T inverse? T inverse is defined as the controllability matrix CAV multiply another matrix W. Controllability matrix here is an n cross n matrix, because we are dealing with seesaw systems here, and W is also an n cross n matrix, and W is given by this form. Now, what is this matrix? Notice that this has a structure here, okay. This has a structure here, and the elements here are the coefficients of the characteristic polynomial of A. Okay. So, we will use this transformation like in the diagonal or the Jordan canonical form, where we used T matrix as the eigenvectors or chain of generalized eigenvectors. In this case, we will use the T inverse definition in this form. Okay. So, remember in that case we had a model matrix that we formed, and then we defined T inverse as that model matrix, right. In this case we are defining P as T inverse, and P is defined in this way. Fine. Let us see how does this help us. Now, you can see that since I have defined T inverse as P, so the same this transformation can actually be written in terms of P also. Okay. So, I can just write down it in this form also. So, in that case A hat becomes P inverse A P, B hat becomes P inverse B, and so on. So, let us see what happens when we try to find out P inverse A P. Okay. So, remember again P is nothing but T inverse, but again here where we are taking T of x of t is equal to Z t, okay, or in other words this is exactly same as P of inverse of this is equal to Z t, which means x of t is equal to P of Z t. Now, here you see this is our P. Now, what is P inverse A P? P inverse A P is, I am calling the matrix to be A hat. So, I can write A P is equal to P of A hat. So, now let us try to find out how this will pan out. So, our objective is to find out how does A hat look. Okay. So, let us look from the left hand side. We will start with the left hand side. The left hand side is A P, A into this is your P, this is the P matrix. So, I have written that, and then what we can do is on the right hand side we have P A hat. So, this is P hat, we want to find out this A hat matrix. Fine. Let us have a look at that. Now, the left hand side A P, this is A P is equal to this. So, we will get this, and now I can multiply this part. Okay. If I multiply this, I will get this A B, A square B, A to the power of n B. Now, notice here that if I multiply this again, I will get an expression like this, alpha 1 times of A B plus alpha 2 times of A square B, and so on. So, the expression will come out to be this. Now, we will use some identities. Okay. Now, remember chi of A, we are calling it to be the chi of S is the characteristic polynomial, which was nothing but alpha naught alpha 1 S plus dot 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 alpha n minus 1 s to the power n minus 1 s to the power of n, and we are now finding chi of A. Chi of A is alpha naught I plus alpha 1 A plus dot 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 alpha n minus 1 A to the power of n minus 1. Okay. Now, we are finding chi A multiplied by B, which will be nothing but alpha naught B plus alpha 1 A B plus dot 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 this expression. Okay. So, there should be an A to the power of n here also. Now, once I find this expression, I can rewrite this expression. See, on the left hand side chi of A will be 0, right, Cayley-Hamilton's theorem. So, I can rewrite it in this way. Now, notice what is minus of alpha naught B, minus of alpha naught B will be this. Now, how does that help us? That helps us because this entire expression, because there is an A to the power of n sitting over here, you can see I can actually go ahead and replace this entire thing by minus alpha naught B. Now, I am calling this to be the left hand side equation number 1. On the right hand side, what is happening? So, this is our equation number 1 that we got, this is the left hand side that evaluated to. On the right hand side, we are finding P of A hat. Okay. So, what is P of A hat? P of A hat would be, P of A hat will be, this will be your P, this will be your P, and this will be your A hat. Okay. So, if it is P of A hat, then if we multiply it out, what do we get? this is what I will get if I multiply this part out. If I multiply this out, this is what I will get, and notice what will this come out to be. I know that this part, this equation and this equation must be equal to each other. So, this is what we get. So, the left hand side must be equal to the right hand side. So, this equation must be true. Okay. So, let us see what happens from there. So, the left hand side and the right hand side must be equal. So, from here what do we get? You see, I have to write down alpha hat in such a way that it multiplies with the first column to give me the left hand side's first column, and so on. So, let me take it up here. So, now notice that I need minus alpha naught b here, and if I multiply these columns. So, these are column vectors, right, these are column vectors. Okay. Now, if I multiply 0 times of first column vector plus 0 times of second column vector dot 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 minus alpha naught times of this will give me the first column, and that is what is being written here. Okay, this gives me the first column of A hat. What is the second column? So, the second column, this has, so what is the second column here is, this is the second column. I have to come up with the second column here. So, what is the second column? Minus, so this is alpha 2 AB I have to find out. So, if I have to find out alpha 2 AB, so this is alpha 2 AB, then we will have up to, so this is the term that I have to find out, but I have to subtract this part out, right. So, basically I will take, you can see the first column here 1 multiplied by this 0 0 0 minus alpha 1 multiplied by b will give, will cancel out minus alpha 1 b with this one, and I will be left with the second column. So, in this way if you keep on going, these are the, this will be the matrix that you will get. So, your A hat matrix will look something like that, and look at this matrix. This is a nice looking matrix in the sense that the top part here, the n minus 1 rows here has a nice structure. The last row here depends upon the coefficients of the characteristic polynomial. The characteristic polynomial was, this was the characteristic polynomial of, this was the characteristic polynomial of A, right, and see the last row here is nothing but the coefficients of the characteristic polynomial. Okay. So, my A hat is in this nice form now. What about B hat? So, again what will be B? B hat will be P inverse B, right. This is what has to be followed, but we know that that means that this must be true, P must be equal to P B hat. So, this is your P, this is your B hat, and on the left hand side you have B. So, now this is your P and this is your B hat. So, I have to come up with a B hat here that will give me B. So, if I come up with 0 0 1, see if I put 0 0 1 here, then this basically gives me this column. If you multiply 0 0 1 with the matrix, and this column multiplied by this matrix will give me the first column out here. Okay, and that is why B hat will come out to be of this form. Again remember, these are column vectors because we are dealing with seesaw case. This is an n cross n matrix here, this is an n cross n matrix here. These are column vectors, so I can always directly write it down in this way. So, A hat and B hat will come out to be in this nice form. Okay. So, what have we done? Again to recap, what have we done? We had the system x dot equal to ax plus bu, then we came up with a transformation pz equal to x. In other words, if I have to link it up with the transformations that we were defining from the beginning of this part, which was basically z of t is equal to t of x of t, and I took t to be equal to p inverse, therefore, pz must be equal to xt. Now, P is defined in this way, which is basically multiplication of the controllability matrix with this matrix. Again, this matrix is formed by the coefficients of the characteristic polynomial. Remember that alpha naught is not present in this matrix, you can see that. Okay. Alpha naught, this is formed without alpha naught. Okay. Now, once you have formed this matrix, then on transformation your P inverse of AP or A hat, this was your A hat, your A hat will come out to be of this form, or in this case I am calling it A bar. So, A bar will come out to be of this form and this will come out to be of this form, B bar will come out to be of this form. See, this namings A bar or A hat depends on you can call it anything, but the idea remains the same. Okay. So, you do not even have to do this calculation, because the way P has been constructed, you can directly write down what will be A bar and B bar, and this will be the A bar and B bar, and this canonical form is called phase variable form or the controller canonical form. Okay. Remember that this form can only be, we can only get to this nice form if the system that we are taking is a controllable system. So, controllability is an assumption, and this whatever we have done here is for CISO case only. So, with that assumption we can come up with this form. Okay. Now, how does it help us? Remember, we were trying to form this minus K1, K2 x. Remember, I started this lecture with that motivation. So, suppose I find I give a control law of the form u equal to, say I call this part as k hat, okay, u equal to minus k hat z. Now, what will happen? So, go ahead and plug it in here, u will be replaced by this equation. So, this is what it becomes. Now, if you multiply this part, the matrix that will come out to be of this form, and now you can add them up, and this is the matrix that you get. Notice the top part here is 0. So, it is not going to affect this part, only the bottom part here minus alpha naught minus k hat naught, in this way they will sum up, and this will be the matrix you will get. And the important thing to notice here, that this matrix is also in the phase variable form. This matrix was in the phase variable form. If the matrix is already in the phase variable form, just by looking into the phase variable form, you can tell what the characteristic polynomial would be. In this case also, just by looking into this phase variable form, you can say that the characteristic polynomial of this matrix that you have found out, this new matrix, this is a new matrix that you have found out. For this matrix, the characteristic polynomial will be this, and once you know that this will be the characteristic polynomial, you just have to change the value of k terms here, so that you can get to the desired characteristic polynomial, the polynomial that you want. Okay. And you can see that in this case it has become such an easy way to solve the problem. I just have to go from this form to this form, and once I go to this form, I can easily find out the value of k hat. Now, if I find out the value of k hat, you can see the control law is u equal to minus k hat. So, this is minus k hat z of t, but we are not solving the problem in z, right. Z was a transformed variable, it is in the transformed it is a transformed state variable. I have to get back to x. So, to get back to x, I can just do p inverse of x, because I know that p of z is equal to x. So, my final k matrix, this will be my final k matrix. So, this part I can call to be the k matrix. Okay. So, the final control law would be of this form, u of t will be equal to minus k x t. Okay. So, let us take an example and try to figure out what we have been doing. Okay. Suppose you have this system x dot equal to x plus b u and y is this. Now, the problem statement is find a state feedback control law of the form u equal to minus k x, such that for eigenvalues, the eigenvalues of the new systems are at minus 2 plus minus j 4 and minus 10. Now, the eigenvalues of this matrix are not at these positions. I want that the eigenvalues of this matrix should be at minus 2 plus j 4 and minus 10. You can check what the eigenvalues of this matrix are, you will find that they are not exactly at these points. Okay. Now, the question is what should be a k matrix here, so that I can change it to that form. Again, remember what is the dimension of k? This is a 3 cross 1 matrix, B is a 3 cross 1 matrix. So, k must be an 1 cross 3 matrix, so that when you plug it in here, since it is x dot equal to a x plus b u. So, when you plug it in, you can notice that when I plug u to be equal to minus of k x, so I get a minus b k whole x, right. So, here b k will be a 3 cross 3 matrix, A is a 3 cross 3 matrix. So, A minus b k is your new state matrix, okay, and changing k is changing that matrix. Okay. So, that is what we are trying to do here. Now, the question is how do I get to a K matrix, how do I find a K matrix such that A minus B k that I was talking about has eigenvalues at these points, and we will try to do that using the idea that we have just now learned. First check whether the system is controllable, because if the system is controllable then only you can use this idea. So, you can quickly check controllability. In the last lecture itself we have seen that if we find out the rank of the controllability matrix is full, that means in this case it is 3. So, hence the system is controllable. So, next we will transform this system to the controller canonical form. To transform this system to the controller canonical form, I need the P matrix. So, to form the P matrix, I need the characteristic polynomial of this matrix, and the characteristic polynomial of this matrix will come out to be this. Okay. You can check this in MATLAB also. You write down the A matrix in this case this way, you can find out the characteristic polynomial in this way. So, if you define the the symbolic, you have to use a symbolic variable. So, sims s, so I have defined s, then determinant of si minus a will give you the characteristic polynomial, and you can see that this is the characteristic polynomial of the A matrix. Once I have the characteristic polynomial, again what is this? This is alpha naught, this is alpha 1 and this is alpha 2, right. So, once I have that, I can use the characteristic polynomial and form the P matrix. The P matrix will be given by CAB into W, CAB is B A B A square B, and my W matrix will be this. Again this was your alpha naught, this was your alpha 1, this was your alpha 2. So, I can go ahead and write down the matrix. So, this will be the matrix and final expression of P will be this. You can go ahead and check that with this P actually you will get P inverse of AP to be exactly what we desired. You can see I will show you in MATLAB. So, this is my P matrix, and you will see that if I do P inverse of AP, exactly you are getting the controller canonical form that we desire. So, this will be the controller canonical form and B matrix will be 0 0 1, right. We know that actually this part you do not even have to do, because you have created P in such a way that you will always get this controller canonical form, but just to show you that yes, this is true, what we have done is correct, I am just showing you this step. Okay. So, once we have done that, our P inverse of AP will come out to be this matrix, this will be your A hat matrix and this is your B hat matrix. Remember, we started the system with state variable x, but now we have transformed the system to state variable z. We will solve the problem using state variable z and then we will go back to the actual states again. So, now I have to come up with a u such the control law here, so that we get to the desired eigenvalues. So, what are our desired eigenvalues? These are our desired eigenvalues. So, if these are our desired eigenvalues, so let us see what the desired characteristic polynomial is. Since these are our desired eigenvalues, so the characteristic polynomial that we are desiring is this s plus 2 plus j 4 plus s plus 2 minus j 4 s plus 10. If this is the characteristic polynomial of the new matrix, then I know that the matrix has eigenvalues at these three locations. And if you multiply it out, this is the matrix that you get. Now, notice that means that the desired matrix, I want that the matrix should look like, right now the matrix is looking like this, but I want that the matrix should look something like this. If the matrix looks something like this, I will know that the eigenvalues have been placed at these points. Okay. So, I will use a control law minus k hat z in this way, and so now my k will be in 1 cross 3 matrix. So, these are the 3 elements that I have to find out, and this A minus B k hat must be equal to this matrix, right. Now, I just have to find out the value of k 1 hat, k 2 hat and k 3 hat, so that I get it. So, if you multiply this out, this is what you will get. You just have to equate the rows here to get the values of k 1 hat, k 2 hat and k 3 hat, and that will come out to be 192, 70, 192, 40 and 2. And once you have, you see, once you have the k hat, so once you have the k hat, you can directly find out the actual control law, because I have to find out the control law in terms of x. So, you can actually go ahead and find out the control law. The control law would be k p inverse x, and then if you multiply this out, your final expression will come out to be this. So, here is your final control law. So, the final control law will be this. again just by multiplying this you will get this. So, therefore, the final control law is this. Let us see whether this works or not. If you look at this A, B and K, and now if you go ahead and check the eigenvalues of A minus B k, you see it is placed at -2, plus minus j4 and -10 exactly. So, this is a simple way by which you can go ahead and change the eigenvalues of the state matrix. What is the advantage of this way? By using this you have changed the response, the state response, because now you see, now think about it, what have you done? You have basically, you had a system x dot equal to Ax plus Bu. This was your original plant, okay. You took the system, you did modeling, you can find out transfer function or state space equations. In this case we are dealing with state equations. So, you wrote down the state equation. So, you got this system x dot equal to x plus Bu and Cx plus y equal to Cx plus du. So, this is your plant. Now, as your plant, so you can find out the state expression xt and you can also find out the output yt, right. Now, the question is, suppose for example, the A matrix that you had, suppose this A matrix you had eigenvalues say 1 and 2. Suppose the eigenvalues of the A matrix was 1 and 2, which means when you will solve this expression, solve for the differential equation, you will get terms of e to the power of t and e to the power of 2t in the response of the system, in the state response and the output response of the system. But you know that e to the power of t and e to the power of 2t blows out, right. As t tend to infinity they become unbounded, okay. That means this becomes an unstable system because the eigenvalues are on the right half of the complex plane, and which means that when you solve this x for the output response and the state response, you will get trajectories which becomes infinite as t tending to infinity. So, we have a problem, suppose, okay. So, that means now you would like that the eigenvalues of the state matrix should be changed in some way, so that I can make the response of the system die down to 0 say at t tending to infinity. So, I have to change the system in some way. Of course, the matrix's eigenvalue you cannot change, you have to change the matrix itself, okay, if you have to change the eigenvalues. So, how do we change the matrix itself? So, we are introducing this control law u equal to minus kx. Why are we calling it a control law? Because we are defining what the input would be, and the input is dependent on the state of the matrix, and that is why we are calling it state feedback, because in this case the input that is going to the system depends on the state, which we are checking what the state is, we are taking that state, multiplying with a k matrix with a negative sign, and then we are giving it back into the system. That is why we are calling it state feedback. So, if I use this, what happens? If I use this, then my system gets changed to x dot equal to Ax plus b minus of kx, which means this becomes a minus bkx, and my output equation becomes Cx plus d minus of kx, that means my output equation becomes C minus dkx. So, you can see that with the help of k you are changing your x, and once you are changing your x, your y also will get changed, because what will be the solution of x dot equal to a minus bkx? The solution of that would be x of t equal to e to the power of a minus bk whole into t x of 0 say. Suppose initial condition is at t equal to 0. So, once you have this solution, you can see that it will depend on the matrix exponential e to the power of a minus bkt, and you know that how to find out the matrix exponential, and the terms that we will get will depend upon the eigenvalues of e to a minus bk, right, the exponential terms that you will get, and which means if I change the eigenvalues of a minus bk to be on the left half of the complex plane, then I know that the exponents will die down to 0 as time tends to infinity. So, this way actually what we are doing, you can see, right, we had a system which when we started off with was unstable, in the sense that it was becoming unbounded, the trajectories were becoming unbounded at t tending to infinity. But now with the help of k, we have changed the eigenvalue positions to the left half of the complex plane, which means that the eigenvalues are dying down to 0 now. Okay. And again, as I was telling, in this case the feedback is state. Okay. In the previous case, in the PID case we are taking the output as feedback and finding out the error signal and then putting it into the PID controller, and then from the PID controller we were getting the U that goes into the plant. Go back to the block diagram, you will remember that. In this case we are taking the states and then feeding it back into the system using the control law U equal to minus Kx, and that is why this is called a state feedback controller. So, I hope that you have understood how to find out the K matrix. Now, actually there is a much easier way to find out the K matrix, okay, and that is what is known as Ackermann's formula, and we will look into that formula in the next lecture. Thank you.